Over 4 billion years ago, our sun was a feeble beacon in the cosmos, emitting only about 70 to 75% of the light and heat it bathes Earth in today. Imagine standing on the surface of our young planet, gazing upward at a pale, diminished star. The sunlight would be faint, the skies dimmer, and the warmth far less intense. Given this faint solar output, the laws of physics suggest Earth's surface should have been an endless winter, a frozen world locked in ice, devoid of oceans, rivers, or any hope for life. Yet, as geologists uncovered clues etched into ancient rocks and minerals, a paradox emerged. Earth was warm enough to sustain liquid water and early microbial life. This conundrum, known as the faint young sun paradox, challenges our understanding of planetary climate, stellar evolution, and the origins of life itself. To understand the paradox, we must first understand our star, the sun, not as it is today, but as it was in its youth. The sun, like all stars, was born from a cloud of interstellar gas and dust, collapsing under gravity and igniting nuclear fusion in its core. Early in its life, the sun burned hydrogen into helium but had not yet reached its main sequence brightness. Over the first billion years, it gradually brightened, slowly increasing its energy output. This dim, youthful star meant that early Earth received significantly less solar energy. Theoretically, with 25 to 30% less heat reaching the surface, temperatures should have plummeted below freezing, rendering oceans solid and life impossible. Yet the geological record tells a different story. Sedimentary rocks from this era, rich with minerals formed in liquid water, reveal a planet with flowing rivers and shallow seas. How could Earth resist freezing under a dim star? The answer lies in Earth's atmosphere, the invisible, gaseous envelope surrounding the planet. Unlike today's relatively oxygen-rich atmosphere, Earth's primordial atmosphere was thick and heavy with greenhouse gases such as carbon dioxide, CO2, methane, CH4, water vapor, H2O, nitrogen, N2, and traces of ammonia and hydrogen. Greenhouse gases function by trapping infrared radiation. When sunlight warms the Earth's surface, the planet emits infrared heat. Greenhouse gases absorb this heat, preventing it from escaping into space, thus warming the surface. Carbon dioxide, released in massive quantities by volcanic activity, was likely a dominant greenhouse gas. However, scientists found that even a dense CO2 atmosphere might not fully explain how Earth stayed warm enough for liquid water. This realization led researchers to investigate other greenhouse contributors. Methane stood out. Methane is an extraordinarily efficient greenhouse gas, about 25 times more potent than carbon dioxide over a century, and even more powerful in the shorter term. But unlike CO2, methane is mostly produced biologically, not geologically. In Earth's oxygen-poor early environment, methanogenic archaea, microorganisms that thrive without oxygen, flourished in swamps, hydrothermal vents, and shallow seas. These tiny life forms produced methane as a metabolic byproduct, pumping this powerful greenhouse gas into the atmosphere. This methane, combined with carbon dioxide, formed a synergistic greenhouse effect, thickening Earth's atmospheric blanket and raising surface temperatures despite the faint young sun. Earth's climate was not static, but part of a complex, self-regulating system. One crucial feedback involved chemical weathering. Silicate rocks exposed to the atmosphere react with carbon dioxide dissolved in rainwater, slowly removing CO2 from the air and depositing it as carbonate minerals in the ocean. When Earth warmed, weathering rates increased. pulling CO2 out of the atmosphere and cooling the planet, a natural brake on overheating. Conversely, if Earth cooled, weathering slowed, allowing volcanic emissions to build up atmospheric CO2 and warm the planet again. This feedback loop acted like a thermostat, stabilizing the climate over millions of years and keeping conditions suitable for liquid water. Water vapor, Earth's most abundant greenhouse gas, further amplified warming through a positive feedback loop. As temperatures rose, more water evaporated, adding moisture to the air and trapping more heat. Clouds, however, present a double-edged sword. Low, thick clouds reflect sunlight back to space, cooling the surface, while high, thin clouds trap heat. The balance of these cloud types and their distribution in Earth's early atmosphere adds complexity to climate modeling, making the faint young sun paradox a rich problem in atmospheric science. Research suggests that Earth's early atmosphere was likely thicker and under higher pressure than today. A denser atmosphere broadens the absorption lines of greenhouse gases, making heat trapping more effective. Nitrogen, while not a greenhouse gas itself, contributes to atmospheric pressure and affects gas interactions, enhancing the greenhouse effect indirectly. This thick atmosphere also shielded the surface from harmful cosmic rays and solar wind, maintaining conditions favorable for life. While the young sun was faint in luminosity, it was also highly active, spewing solar flares, intense ultraviolet radiation, and a strong solar wind. These energetic phenomena influenced Earth's atmosphere by ionizing gases, driving chemical reactions, and potentially stripping lighter elements from the upper atmosphere. Understanding this interaction helps scientists model how the atmosphere evolved and how greenhouse gases were maintained or lost. Scientists analyze ancient rocks to reconstruct early climate conditions. Isotopic ratios of oxygen and sulfur in sedimentary rocks indicate the presence of liquid water and atmospheric composition. For example, oxygen isotope ratios reveal temperature ranges, while sulfur isotopes inform about volcanic activity and atmospheric chemistry. The discovery of banded iron formations and other sediment layers provides clues to the oxygenation timeline and how early life impacted atmospheric gases. The faint young sun paradox is deeply intertwined with life's origins. Life not only survived, but helped solve the paradox. Methanogens produced methane, contributing to the greenhouse effect. Later, photosynthetic organisms began producing oxygen, altering atmospheric chemistry and climate. This biological climate feedback highlights the coevolution of Earth and life, illustrating how living organisms can transform their planetary environment. The paradox extends beyond Earth, informing the search for life on exoplanets. Many exoplanets orbit dimmer stars, red dwarfs, and K-type stars, which emit less energy than the Sun. The faint young sun paradox shows that thick greenhouse atmospheres could warm these worlds enough for liquid water, expanding the potential habitable zones in the galaxy. Understanding these processes helps scientists prioritize targets in the search for extraterrestrial life. Studying Earth's early climate teaches us about climate stability and sensitivity. It reveals how greenhouse gases regulate planetary temperatures and how feedbacks maintain equilibrium over geological timescales. This knowledge is crucial as human activities today alter atmospheric compositions at unprecedented rates, risking disruption of climate balances. Despite progress, many questions remain. How exactly did clouds and aerosols influence early climate? What were the detailed chemical pathways maintaining methane? How did volcanic activity vary, and what role did oceans play in carbon cycling? Future research combines satellite data, advanced climate models, laboratory experiments, and planetary missions to Mars, Europa, and beyond, all aimed at understanding planetary habitability and the faint young sun paradox. The faint young sun paradox is a profound reminder of Earth's fragility and resilience. Our planet's warmth in the face of cosmic dimness was no accident, but the result of intricate interactions spanning stars, rocks, microbes, and atmospheres. It challenges us to appreciate the delicate balances sustaining life, to marvel at the cosmic circumstances that made Earth a living world, and to reflect on our responsibility to protect this precious balance.